The James Webb Space Telescope, JWST, continues to make groundbreaking discoveries that are challenging and expanding our understanding of the cosmos. For centuries, scientists have searched for answers to the fundamental questions of existence. How did the universe begin? What is it made of? Are there other dimensions or parallel universes? Now, with the power of the JWST, the first real evidence of the existence of another universe has emerged. This could revolutionize the way we view our universe and force cosmology to evolve once and for all. The discoveries made by the JWST are nothing short of astonishing, and there is still much that remains to be understood about their broader implications. The JWST is not just another telescope, it represents a new era in space exploration. With its 16 gold-coated mirrors, the JWST has an unparalleled ability to observe the universe with an extraordinary level of detail. It has sharper resolution and can see at angles that remained hidden from the Hubble Space Telescope. One of the most exciting things that the JWST allows scientists to do is witness events that occurred shortly after the Big Bang. Its ability to peer back in time has revealed strange points of light in the early universe, mysterious gaps in cosmic background radiation, and enormous black holes that seem to defy the rules of the standard cosmological model. These black holes are so massive that they must have existed before the Big Bang, or could originate from another universe entirely. One of the most shocking revelations made by the JWST was the discovery of fully formed galaxies only 300 to 400 million years after the Big Bang. This is a major surprise because according to the prevailing cosmological models, galaxies should have been chaotic, unordered clouds of gas and dust in the early universe. It was thought that it would take hundreds of millions of years for galaxies to form and become stable. However, the JWST has observed dozens of large, well-structured galaxies from this early time period. These galaxies are much older and more developed than scientists had ever expected, leading some researchers to propose that these galaxies could be remnants from an earlier universe. This discovery offers strong support for a theory called conformal cyclic cosmology, CCC, proposed by British physicist Sir Roger Penrose. Penrose's theory, which he published in 2015, suggests that our universe is just one in a long series of cyclic universes. When one universe reaches its end and dies, a new one is born in a process of cosmic rebirth. The matter and structures from a previous universe could survive and be transferred to the new universe. This would explain why some of the galaxies in our universe are much older, more advanced than we would expect based on current models. If Penrose's theory is correct, the discovery of these ancient galaxies could be evidence of the material remnants of a previous universe. One of the most profound aspects of this discovery is the potential for a cyclical, eternal process of cosmic rebirth. Penrose's theory suggests that not all structures are destroyed when a universe ends. Some density fluctuations or entire structures of matter might be carried over into the next universe, preserving their existence across cosmic cycles. If true, this would challenge the traditional understanding of the universe's origins and lead to a much larger and more complex model of cosmic history, one where the Big Bang is not the beginning of everything, but just one phase in a continuous cycle of birth, death, and rebirth. The JWST has also contributed significantly to our understanding of the cosmic microwave background, CMB, the faint afterglow of the Big Bang that permeates the universe. The CMB is the oldest light we can observe and offers crucial insights into the early universe. The JWST has enabled scientists to explore irregularities in the CMB that were previously difficult to study. These irregularities include larger gaps, colder regions, and mysterious temperature patterns that do not fit the standard cosmological model. One of the most intriguing explanations for these anomalies comes from Penrose's theory of Hawking points. Penrose believes that these unusual temperature patterns in the CMB could be the remnants of supermassive black holes from a previous universe. According to his theory, black holes slowly evaporate over time through a process known as Hawking radiation. When a universe reaches the end of its cycle, the black holes within it slowly dissolve, leaving behind nearly empty space. This residual energy, left over from the previous universe, could provide the signatures of a past cosmos. If the temperature patterns observed in the CMB are indeed Hawking points, it would represent a groundbreaking confirmation of Penrose's conformal cyclic cosmology. In addition to the findings in the CMB, the JWST has also provided compelling evidence of supermassive black holes that existed in the early universe, just a few 100 million years after the Big Bang. This discovery is particularly puzzling because black holes of such size typically take billions of years to form. Black holes usually form from the collapse of massive stars, or they grow slowly by accreting gas and dust over time. However, the JWST has detected supermassive black holes that are far too large to have formed in such a short period. Some researchers speculate that these black holes may have survived the end of a previous universe, potentially carrying over from one cosmic cycle to the next. These findings provide further support for Penrose's theory that our universe is part of a much larger, eternal cycle. The JWST has also observed accretion disks around these supermassive black holes, indicating that they are actively feeding on surrounding matter. This raises further questions, as the early universe should not have contained enough stars and gas to sustain such massive black holes. It's possible that we are witnessing the interface between different universes, with objects from multiple universes overlapping, and interacting at this stage in the universe's evolution. If different universes can indeed collide or overlap, the resulting interactions could create anomalies that challenge our understanding of physics. Another significant discovery made by the JWST involves a mysterious cold spot in the cosmic microwave background radiation. This cold spot is unusually large and too cold to be explained by the quantum fluctuations typically seen in the early universe. Scientists have long puzzled over the cause of this cold spot, and some believe that it may be evidence of a collision between our universe and another. If this theory is correct, it could provide the first direct evidence of a multiverse, the idea that our universe is not an isolated entity, but part of a vast and complex web of many universes, each with its own laws of physics. In a multiverse, there could be universes with entirely different properties, such as universes with different forms of matter, antimatter-dominated universes, or even universes where time flows backward. If our universe collided with another in its early stages, the resulting interaction could have left traces in the cosmic background radiation. The JWST is currently being used to study distant galaxies and structures within the cold spot, searching for unusual matter distributions, strange light patterns, or signs of physics that cannot be explained by current models. If any such anomalies are found, it could provide strong evidence that the cold spot is the result of a collision between universes. The JWST has also confirmed long-standing issues with the expansion of the universe. For decades, scientists have noticed discrepancies in the expansion rate of the universe, a phenomenon known as the Hubble tension. This suggests that the universe may not be expanding uniformly, as was previously assumed. Some researchers propose that the different expansion rates could be due to the influence of another universe, which could be distorting the expansion of our own universe. Alternatively, the universe could be a bubble within a multiverse, where different regions experience different laws of physics, leading to different expansion rates. Finally, the JWST has revealed extremely bright objects in the early universe, objects that are far too bright, massive, and young to fit within existing models of galaxy and star formation. These objects, which appeared just a few 100 million years after the Big Bang, are much brighter than scientists expected. One possible explanation is that these objects are early quasars, powered by supermassive black holes. However, even quasars should take hundreds of millions of years to form, and these objects appear to have formed much faster than expected. This raises the possibility that these objects could be a completely new type of celestial body, potentially related to unknown physics or even remnants of a previous universe. The discoveries made by the James Webb Space Telescope are reshaping our understanding of the universe in profound ways. With each new observation, the telescope challenges existing theories and opens up new possibilities for the existence of parallel universes, ancient black holes, and strange anomalies in spacetime. As scientists continue to analyze the data, it is possible that they will unlock even more secrets about the cosmos, leading to new theories of cosmology that could change the way we view reality itself. The JWST is not just a tool for observing space, it is a key that could unlock the deepest mysteries of the universe.